Hi folks, Chris McClure. We're going to now talk about logarithms, which are inverses of exponentials, as we shall see. So here we go. So imagine instead of having y equal to a raised to the x power, and we swap x with y, where we have this. So how can you define y so that you can get y expressed explicitly in terms of x? Well, we can do that by defining what is known to be a logarithm, or as a function we call it a logarithmic function, where y is that function such that y is explicitly written as a function of x. And here's what this looks like. We have this logarithm, log, is the function with a certain base, a, where a could be 2 or 5 or e or pi or 1/2 or any other positive real number. And when we say that y is the log base a of x, that's the same thing as saying x is equal to a raised to the y power. So these two functions are exponentials, and logarithms, they are inverses of each other. When you take the logarithm of a number, you're really looking for that exponent such that a raised to that exponent, in this case y, is what x is. So for example, if I say that log base 3 of 81 is equal to 4, that's the same thing as saying that 3 raised to the 4th power is equal to 81. Or if I say that log base 5 of x is equal to y, that's the same thing as saying that x is equal to 5 raised to the y power. Or in other words, as an example, suppose that instead of x we have 1/5. Well, guess what? 1/5 raised to the negative 1 power is equal to 5. So 1/5 is equal to 5 to the negative 1 power. So, and 5 raised to the negative 1 power is equal to 1/5. So what you do is you just look at the base here, that's 5, oops, and then raise it to this power, and you'll get this number right here. So you're just basically doing a puzzle. This base raised to this power is equal to this argument of the log function. So and we can always go back and forth between logarithms and exponentials. For example, if I say that 1.2 raised to the 3rd power is equal to m, well, that's the same thing as saying that log base 1.2 of m, whatever that is equal to 3. The 1.2, that's the base of the logarithm as well as the base of the exponentiation. The 3 exponent is the result of taking the logarithm. Okay. Now, what about e to the b being equal to 9? Well, that's the same thing as saying that b is equal to log base e of 9. And by the way, we defined e in the previous lecture. E is that very special number. And as we're going to see here in a minute, that the log base e appears so often that it gets its own notation, ln, as in the natural logarithm. If we have a to the 4th is equal to 24 for some number a, that's the same thing as saying that log base a of 24 is equal to 4. Or if I say that log base a of 4 is equal to 5, that's the same thing as saying that a to the 5th power is equal to 4. And if I say that log base e of b is equal to negative 3, that's the same thing as saying that e to the negative 3 power is equal to b. And if I say that log base 3 of 5 is equal to c, That's the same thing as saying that 3 to the c power is equal to 5. All right, do you see the connection between logs and exponentials? Well, let's talk about evaluating log expressions here. What would be the log base 3 of 81? What you're looking for is the exponent on the base 3 such that 3 raised to that exponent is equal to 81. So we know that 3 to the 1 power is 3, 3 squared is 9, 3 to the 3rd power is 81, and indeed 3 to the 4th power is 81. So the value of this logarithm here really is 4, huh? So the value here is 4. What is log base 2 of 1/8? Meaning 2 raised to what power is equal to 1/8? And the answer is -3. So log base 2 of 1/8 is equal to -3. Okay? Now, remember the relationship between domain and range functions and their inverses? The domain of the one is the range of the other and vice versa. And we talked about the domain of the log function being the set of all positive numbers. Well, that's the range of the exponential function, so that automatically means that since the range of the exponential function is the set of all positive real numbers, then that's going to be the domain of the logarithm, because of the fact that the exponential and logarithm functions are inverses of each other, and vice versa for the range of the log being equal to the domain of the exponential function, which is the set of all real numbers. So here we've got the formal statement of the domain and the range of your basic log function, regardless of the base. As long as a is some positive number, the log base a of x function has a domain of all positive real numbers, because, by the way, it doesn't make the sense to take the logarithm of 0 or negative numbers. But the outputs of the logarithm could be any real number, including negative ones. What would be the domain of this function right here, log base 3 of x minus 2? Well, we know that the domain of the log function is the set of all positive numbers, so you set x minus 2 to be positive, which means that x is greater than 2. So any value of x which is greater than 2, you could take the logarithm of it. So that would be the domain of this function for part A. For part B, what's the logarithm of this function here? Well, look, all you need to do is solve the equation, set this rational function here, the x plus 3 over x minus 1, set that to be greater than 0. And then you can go back and use your techniques for solving rational inequalities. But it turns out that between negative infinity and negative 3, together with 1 to infinity, will be the set of values of x, which will make this rational expression be positive, and thus be the domain for this log function. What is the domain for this function here? Log base 2 of absolute value of x minus 1. Well, look, as long as you're not taking the logarithm of a number that's either 0 or negative, then you're good. Well, look, for the absolute value, that result is never negative. So your only concern now is just whether x minus 1 is 0. That's only going to happen when x equals 1. So any other real number besides 1 will work. So you could write this as the domain for this function right here. Here's the domain. All real numbers except for 1. All right, graphs of logarithms, well, they should be mirror images of graphs of exponentials. So, first of all, if the base is between 0 and 1, the graph of a to the x looks like this, if you remember from previous discussion. Then the mirror image of that would be this purple graph, where you just are swapping the x and y coordinates of all the points from a, or a raised to the x power. Here in the second graph, we have the graph of y equals a to the x, where a is greater than 1. And of course, the mirror image of that graph with respect to the y equals x axis is going to be this one right here. And this is pretty much what the graph of most logarithms look like. We very rarely deal with logs with fractional bases, meaning with bases less than 1. For most of my experience, we deal with logarithms with base that's greater than 1. And there's what the graph generally looks like. It goes through this point, 1 comma 0, and it goes from the negative infinity, which the function approaches as x approaches 0 from the right, goes up and up through 1 comma 0 and up to the upper right. Like, for example, the graph of y equals log base 2 of x. Here's the graph of y equals log base 1/3 of x. Okay. So, for your basic logarithm function, regardless of the base, the domain is a set of positive real numbers. It doesn't make sense to take the logarithm of 0 or a negative number. The range of the logarithm is a set of all real numbers. If you take the logarithm of a number that's between 0 and 1, the result is going to be a negative number. The x-intercept of this function here is going to be 1. And log of 1 is 0, regardless of the base, because a raised to 0 power is 1. The log function has no y-intercept for the graph. The graph has no y-intercept. The y-axis is the vertical asymptote of the graph, either upward or downward, depending on whether a is less than 1 or greater than 1, respectively. But regardless of what a is, as long as a is either less than 1 or greater than 1, the graph of the function always includes these 3 points. By the way, what would log base 1 of x be? So that would be 1 raised to any power is equal to 1, huh? So that wouldn't work very well, will it? Because suppose that you're taking log base 1 of 2, for example. Well, 1 raised to what power is equal to 2? The answer is you can't solve that. So that's one reason why it doesn't make sense to have a log base 1. So that base is either less than 1 but greater than 0, or greater than 1 but not ever equal to 1. And the graph of your logarithm function is always going to be nice and smooth with no corners, no gaps, no holes, no sudden jumps or anything like that. Remember the natural logarithm function? That's log base e with the special notation ln. So ln of x, that's the same thing with log base e of x. So we say y equals natural log of x if and only if e to the x, or e to the y is equal to x, I mean. And here you can sketch the graph of it. But hey, the graph of the natural log function looks just like the graph of any other logarithm function, provided that the base is greater than 1. It still goes from the lower left to the upper right, with the y-axis acting as a vertical asymptote. So what would the graph of negative natural log of x minus 2 look like? Well, hey, we could just start off with the graph of y equals natural log of x, and then we can put a negative in front of it, which would reflect the graph about the x-axis, turn it upside down essentially, and then replace x by x minus 2, which shifts the graph 2 units to the right. So, and the inverse will just be the exponential. Okay. All right. So, and of course, you can graph it just by reflecting about the line y equals x. And remember, the domain of this function right here will be the range for its exponential twin. All right, moving along here. Now, if you were to see just log of x without there being a mention of any base, just assume that the base is 10. Our number system is a base 10 system, and in a lot of applications, it makes sense to use a base 10 logarithm. And we can go through the same sort of discussion here as we did for the previous example. Hey, what's the graph of this function here look like? 3 times the log of x minus 1. Well, just start off with the graph of log of x. That's log base 10 of x, by the way. And then, modify it by maybe replacing x by x minus 1, and that shifts it 1 unit to the right, and then multiplying by 3, which will do a vertical stretch by a factor of 3. You can graph these more complicated log functions just by starting off with the graph of the basic log function, and then one step at a time do your transformation. And we can talk about the inverse with the graph. Well, that's just going to be the reflection about the line y equals x. The domain of this function right here will be the range of the inverse. And yep, and we graph the inverse reflected about the line y equals x. We can talk about solving logarithmic functions just by understanding the relationship between exponentiation and logarithm. Suppose that we've got log base 2 of 2x plus 1, and that is equal to 3. Well, what is x in order to solve this equation? Well, what we could do is we can exponentiate with base 2. So take 2 raised to the log base 2. So that, because look, log base 2 of 2x plus 1 is being set equal to 3, and that means that 2 cubed is equal to 2x plus 1. But 2 cubed is 8. Subtract 1 from both sides and divide by 2, and you get x equals 7/2. And of course, you could always check your answer just by plugging that 7/2 back in for x. And indeed, 2 times 7/2 is 7, plus 1 is 8. Log base 2 of 8 is 3. And indeed, we have 3 on the right-hand side of the equation. So there, we just checked our work. It's always a good idea to just take an extra minute to check your work if you have the time. How about log base x of 343 equals 3? What does x have to be in order for this equation to be true? So what we're saying here is that x raised to the third power is equal to 343. So what cubed is equal to 343? And then, of course, the answer is 7. You could take the cube root of 343 and you get 7. And you could always check your work and verify that log base 7 of 343 is equal to 3, because 7 cubed is equal to 343. Now, suppose that we have this equation involving the exponential. 2 times e to the 3x is equal to 6. What does x have to be in order for this equation to be true? Well, you could divide both sides by 2 to get the exponential by itself. And then, look, e to the 3x equals 3 means that natural log of 3 is equal to 3x. Natural log of 3 is just a number. Divide both sides by 3. So you got x is equal to natural log of 3 over 3. And then you can plug that into your calculator, and that approximately is 0.366. By the way, let me pull up my calculator so we could talk about how to evaluate logarithms. Now, in particular, your natural logarithm is got by this number here, the ln, by this button there. So if you want to do natural log of 3, and just plug in your argument there, and then hit your closing parentheses, and hit enter. And then if you want it to divide by 3, then go ahead and divide by 3, and you get 0.366. If you want to do log base 10, there it is. So if you want to do log base 10 of, say, 1,000,000, and you'll get 6, because of the fact that 10 raised to the 6th power really is equal to 1,000,000. So no surprise. So, but those are the only sort of logarithms that you see on your calculator: log base 10 and the natural logarithm. And, you know, we could talk about how to do a change of base. So if you wanted to do log base 2 of some number, that we could do that in terms of log base 10 or natural logarithm. We're not going to talk about that today, though. All right. So we talked about how to evaluate this natural log of 3 over 3 to get this approximate solution. Let's talk about blood alcohol content when we're giving a blood alcohol test to someone who we suspect might be drinking and driving. So let's go ahead and read through this. The BAC is a measure of the amount of alcohol in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts of alcohol per 10,000. So 4 per 10,000 parts blood in the body. A relative risk is defined as the likelihood of one event occurring divided by the likelihood of some other event occurring. For example, if an individual with a BAC of 0.02% is 1.4 times as likely to have a car accident as an individual that has not been drinking, the relative risk of an accident with a BAC of 0.02% is 1.4. Recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by the equation of the form e to the kx, where x is the percent of concentration of alcohol in the bloodstream, and k is some constant to solve for. And you can solve for this just by saying that the function goes through a particular point. So, for example, we find that if someone has a 0.02% BAC, that translates to a relative risk of 1.4. So we could plug on the 1.4 for R and plug in 0.02 for X and simplify. Make sure that in this equation, X is the percentage BAC. So you got this equation here, e to the k times 0.02 being equal to 1.4. That's the same thing as saying that natural log of 1.4 is equal to 0.02 times k. So divide both sides by 0.02, and you get natural log of 1.4 divided by 0.02, and that works out to be about 16.82. So now we can go back into the function and replace k by 16.82. And with that value of k, what is the relative risk of the concentration? Is 0.17%. So someone who was very drunk. So going back to the equation, replace the k by the 16.82, which we found earlier, and replace x by the 0.17%, or 0.17. Now, so you got 0.17 times 16.82, enter, and then use that as the exponent on e. And so I want you on your calculators to try this and see that you get 17.5. As in, the relative risk is 17.5 for someone with this high blood alcohol content. They're 17.5 times more likely to get into a car accident at this BAC than someone who hasn't been drinking. Here's another question for you. What blood alcohol content corresponds to a relative risk of 100? So what BAC would you have to be so that you're 100 times more likely to get into a car accident than someone who hasn't been drinking? So just set the function with that appropriate value for k. Set the function equal to 100 and solve for x. So you could take natural log of both sides, so that you got natural log of 100 is equal to 16.82. Remember, when you take the natural log of e to the 16.82 times x, you just get 16.82 times x. So you could take a logarithm with the appropriate base, so as to match the base of exponentiation, so that you could solve for this exponent. And then divide both sides by the 16.82, so you get x is equal to about 0.27. So someone who has a BAC of 0.27%, they are 100 times more likely to get into a car accident than someone who has not been drinking. Suppose that we've got a state law that says anyone with a relative risk of 5 or more should not have driving privileges. So what would our blood alcohol content need to be in order to have a relative risk of 5? So you just set your function equal to 5, like you see here, and then solve for x, just like you did in the previous problem. So take natural log of both sides, divide both sides by 16.82, and x works out to be about 0.096. Okay. So under the state law, anyone who had been drinking and they get stopped and found to have this BAC of 0.096% or higher, they would be arrested and charged with DUI. At least according to this scenario here. I think in every state in the union it's 0.08%, regardless. Let's just quickly summarize the logarithms, the functions that we've talked about today. Log base a of x being equal to y means the same thing as a to the y power equal x. We took a look at the graph of the log function, which is going to look like this, provided that a is greater than 1. If a is between 0 and 1, then the graph is going to look like this. Both scenarios, the curve is really going to go through a comma 1 and 1 over a comma negative 1. And just ask yourself why that's true, and you can work it out. If you're confused, let me know, and I'll work it out for you. The domain of the log function is all positive numbers. The range is the set of real numbers. And that's it for today. We've got one more section to go through. It's the very last section that we're going to cover through the semester. That's in section 6.5. And we'll do that tomorrow. Okay, so that's it for today, and we'll see you tomorrow.